Hi guys, welcome to part 2 of the ultimate guide to reverse engineering a PCB into a schematic. I'll have Detlef with me shortly, who is going to assist me again with this video as he did in part 1. But first, a message from our sponsor PCBway.com. PCBway make a whole range of PCBs. You can see here I have a number of PCBs made by them. These are produced in a number of different styles. For example, this is one that myself and Carlos, Retro Upgrade, designed and uploaded. This is the upgraded $1 short finder. We have other projects which we've worked on. For example, this one is a bench power supply, which we are kind of in progress with. So this is one we will complete shortly or work on more. This is a project we haven't worked on yet. I have a number of PCBs here for forthcoming videos, okay? But you can see that these PCBs are made to extremely high quality. We can have single-sided boards like this one. This is the RF signal generator. I actually built this one, and a lot of you guys were quite impressed with just how well this one worked, okay? So we have this type of PCB. And a whole variety of options, different colours, different styles, rounded corners and such like, as you can see. This one, a Weller soldering iron driver, again another project I will get around to looking at. When we complete our design of the schematic from the PCB today, we are going to have a look at how to modify that. So for example, to build a surface mount version from a through-hole version, which we've reverse engineered. And of course, we will need to order some PCBs, and we're going to do that at PCBway.com. Here are some projects that myself and Detlef and Mend have been working on. You can see we have a HDMI diagnostic board. We have a upgraded version of the USB load that I built on the channel last month. And we also have a soldering iron test PCB. The USB load, basically we are adding facilities such as voltage, current and wattage measurements, possibly some sort of logging facility as well, so you can leave the load running and then later see how the power supply performed. And also we're adding inputs from banana sockets, so you can attach this load to other devices as well as a USB. Add on to that, we're adding PD control, so this is for USB chargers that can provide different voltages, 5, 9, 12, 15, 20 volts, which is controlled by the load. So our load will have a switch on which will allow us to select the voltage we want from the power supply. The soldering iron test, by the way, this is a PCB which has areas on the board having more and more internal power and ground planes from single layer to 8 layer. And these are intended so we can test soldering irons, different ones I've reviewed, and get an accurate comparison between 2 or more different ones. So at the moment I'm using PCBs, scrap PCBs, soldering and resoldering components, but due to variations in the PCB itself, it's difficult to get an accurate idea of the performance of the iron. Some PCBs require more heat or more energy in certain areas to desolder components, and that will vary across the PCB. So this is to get a uniform PCB with different test pads, which we can effectively get a proper comparative test. So now let me show you how to upload one of these. I'm going to upload the USB load to PCBway because this is the next project I want to work on the channel. This is PCBway.com, and it's very simple to get a quotation for your PCBs and to order them. So to do that, initially we just go to quote now, quick order PCB. And we don't need to worry too much about all these various options here. We just need to upload our Gerber file. So we'll add the Gerber file. This is the USB load, open. It's read the Gerber file. And we can actually see a diagrammatic representation of our PCB from both sides. You'll also notice this version, if you can see it on here, it has connections for 4 output transistors, so we can get a higher load, maybe 120 watts from this. And this is where the banana sockets are mounted, okay? So now we have that. You can see we have here shipping costs to my country, which is Spain. I'm using global standard. This is the cost. So this is the cost for 5 PCBs. This including postage. So less than $10 for 5 PCBs. It's showing me a delivery date. If I order now, this will arrive on the 8th of May. If we go to shipping costs in countries, we'll just look, you'll see that in fact PCBway shipped to just about everywhere. You can go down the list and find your territory or country, but they certainly ship to some out of the way places without a doubt. Cayman Islands, I can see here, Cape Verde, Cabo Verde, Curacao, yeah, Djibouti, and where else did I spot on here? Somewhere exotic, Guadeloupe. Yeah, so they deliver just about anywhere. I also have the option of the postage I want to use at different prices. So the one I selected was global standard shipping, but if I'm in a rush and I'm happy to pay the extra cost, I can use, for example, DHL. So this is 3 to 5 business days. Apply. You can see now that the delivery date has come forward to the 1st of May and the price is $33. So it's entirely up to you how you want to handle the shipping. The options really would depend on how quickly you need the PCBs. If I now save this order to my cart, PCBway will review the order. So before I have to pay for my order, PCBway's technicians will review the order. They check the design of the PCB, the Gerber file. They make sure there are no issues in the production of the PCBs. If there are, they will contact me and advise me on any changes I need to make or even help me with those changes. Once the design is accepted and everything is fine, they will then ask for payments, and after payment the boards go straight in production and are shipped to me. If you're interested in prototyping or ordering batches of PCBs, guys, give PCBway a try. There is a discount voucher in the description to this video, which if you are a new customer with a new account, you will get $5 off your order. That means if you use the economy postage, which we looked at, like so, and you are placing your first order, then effectively you're going to pay the postage. The PCBs were free. Yeah. So guys, give them a try. Without a doubt, you will not be disappointed with the quality of the PCBs. I've used a number of them now on this channel for almost a year, and I've not had a single problem. They've all been excellent. Okay, now back to the main presentation. Okay guys, so I'm going to show you now how to connect the points together on the schematic and on the PCB layout. To do this, we have to create what are called nets. A net basically is just a list of points, component legs and pins that are connected to each other. And each net will have a unique name. But the name is arbitrary. It's whatever means something to you. They can be, for example, you can see here, N8, N5 and such like. N4, 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 N4. You can see they're all connected to each other. Or they can be something more meaningful. For example, this is the bridge rectifier. The output across here to the thermistor goes to a net called HT, high tension. Okay, this is the high voltage. You'll notice, by the way, I haven't connected this net across here. The reason for that is because you can't cross the lines. Okay.
Just like in Ghostbusters.
Just like in Ghostbusters. And you'll see actually on the original PCB here, there is a wire link. Now, you could, if you like, create a test point or something similar here on your schematic, one there. So you've got things you can join together, and you can then effectively join those points to the same net. The other thing you could do actually, guys, is make this a double-sided PCB, even though only this side exists, and those wire links can just be tracks on the other side. But for now, we're just going to look at one of the other tracks. So this is the negative end of the bridge rectifier, the negative end of the large capacitor. This is hot ground. So why not call the net hot ground? Okay. To do this, we go to the select tool. I'll zoom in a little bit. We click on the net so it's white, and then we right click and properties. And this tells us that this is an unconnected net, pad 4 of the bridge rectifier. Okay, so we're going to create a net and we're going to give it a meaningful name. So we click in here and I'm going to call this hot GND, hot ground. Okay. It's now asking if we want to create that net. You must remember to do this. Click on it, create net. You'll see there now it shows you hot ground on pad 4 of the bridge rectifier. Okay, and you'll know if it worked because you'll see hot ground. We now need to connect all the other components which are connected on this track together. So this is the next one. Again, left click to select it, right click, properties. And you'll see again it's unconnected. We need to tell the software it's hot ground, but we don't have to create that again. We can literally go to the nets and choose hot ground. You only need to make it once. Okay, we'll do one more. I'm not going to go across this whole track. It goes to many places. 3 will be enough. So we go to this end of this resistor. Can you see now why just putting these in the ballpark is good enough if you want to create a schematic? So left click to select it, right click, properties. Once again, hot ground. Okay. Now you've probably noticed that while I've been clicking on all these points that in the schematic, it's actually showing us where it connects to. We go on to this one. You see? It shows the component. Now, I've selected the entire component is in white, so it's not showing me which pin is connected to hot ground. If I click the actual pad, now it shows us. Okay, so now we need to connect these points all together. I'm not going to go and do everything else on this track. This will show you. I'll leave you guys to spend the time on your PCB. But the way I do this is literally to click on this symbol, add global label, and the name is going to be hot GND. Okay, and I now have a label, and I want to attach it to this point. I actually hit R to rotate it till it's facing the way I want. I click the left mouse button once and then hit W, and I now have a wire, so I can connect that to the capacitor. Now we go to the next component on this net, that's the bridge rectifier. Just click to select it and you can see bridge rectifier is here. Once again, I create the symbol, hot GND. Okay, and I can add that to my bridge rectifier. Rotate, rotate, left click, W for wire, connected. There's just one more point on this track I'm going to add at the moment, and that is this one. Again, R2, I selected it correctly just on the one pin. Now there's a bit of clutter around here, so first of all, I'm going to the arrow tool, I'm going to pick up this component, and I'm going to move it out of the way a little bit, okay? Now I can add my label. Hot GND. Okay, I have it. Auto rotate, left click, W, wire. So that's how I'm adding the components on the net. Now if you look at the PCB, you'll see, and by the way, I've just clicked on the background here, that just brings it to the front. I haven't lost all the work, just click on one of the components, they will all come back again. You'll see the faint blue lines. So because I've only worked so far along this and it's tea time, I'm just going to draw the net as far as I've got, and then I'll know later on where I need to continue from. So to do this, net tool, click in here, go to C small, this one, C1, click on C1 again, and I can bend this. If I want to go around the corner, I just click mouse button once, left mouse button. See, I've come around the corner again. I want to go to here, left mouse button once. And that's now connected. You'll see the faint blue lines have disappeared. So I know exactly how far I've got on this one, and then later on I can start connecting to the other components on this track. Okay, so that's the way I do it. Now I know that Det has a few other tricks up his sleeve, a few shortcuts here. So I'll pass you back over to Det. We'll show you the slightly quicker way of doing that.
Okay, so there's not really much shortcuts that I can do here. The software isn't designed to be used that way around. It's a layout software. Normally you go from schematic to PCB, and what we're doing right now is something that isn't intended to be used that way. So we'll have to live with some complications and some nastiness around.
Okay.
All right. Simply, my way would be, I'm a fan of everything shortcuts. So yeah, I'm a lazy person. Yeah. All right. Let's start with the same as Richard just did. I'm going for this track over here. So there's a TL431 in there. There's a capacitor in here. There's a opto in here. And I'm going for this track right now. So I'm simply selecting the first pin of the R102. You see, at the same time, this gets selected too. So this is really, really helpful. And I only need this side. Now it's selected. All right. Simply do the same as Richard did. I go for properties and give it a new net. So this will be N14. Create net and OK. It says N14. And I had to think, I thought, well, maybe there's a possibility right now if I route a track from here to say there. And no, sorry, it won't work. I can't connect to this track because the router knows that this isn't the same net. So there's no way to connect it over here. This would have been a nice shortcut to simply draw the track and say, this is a point, this is a point, this is a point, this is a point. It won't let you do that. Sorry for that. So we have to do this the hard way around. So this is N14. So N14 is already over here, so I can go there. And the next thing I need is this one. And first shortcut, press E to get to the properties.
Okay.
So N14. Okay. And I need this part of the TL. There it is. E. N14. Okay. So now all of these are connected. You see the blue line over here. This is called a rat's nest because if you have a lot of them, it looks like a rat's nest. Yeah, it's a technical term. Okay, and from here on, pretty much do the same as Richard does with some shortcuts again. So I know here's my TL431 selected. You see this is the pad that we use. So I'll grab a net, and this is called N14. No, it's not called something. This is just N14. Go. And what I do, Richard dropped the net over here and draw a line. I simply go for drop it right on the pad here over there because it's connected anyways. And I don't have to draw the line for here. And the next thing I'm going to do is I simply press Control C because I want to copy this net label.
Okay.
So now it's in the clipboard. I go to C105 and select the connected pad and press Control V and nothing happens.
Oh, why?
I have to select the select items controller over here. And now I can press Control V and there's N14.
Okay.
Rotate, rotate, rotate. Simply drop it there. This isn't beautiful. I know that. But since we're going to mix it up again when we're going for a real schematic, it doesn't matter.
Okay.
So next part, N14. This is on the optocoupler, and you see now all the component is selected. That means I don't have the pad. Now I have the pad. It's pad 2. Control V. Now I have to select the image, the window. Control V. Rotate, rotate. Drop it over there.
Okay.
And one is left. This is the one over here. R102. This is all again the whole component. And this is the part that is left. Click onto window, Control V. And yeah, I'm going to do a wire here because
perfect.
yeah.
Okay, so that's Det showing you a few shortcuts. You can use whichever method you prefer. It's basically down to which way you prefer to work.
Yeah.
Okay.
And don't get this wrong. This takes time. This isn't a thing you can do in 5 minutes. With bigger complexity, you will be spending hours for that. We know because we tried.
Okay. As Det said, guys, this is not a quick process. Expect to spend some hours doing this. So to make this video to a reasonable length, I've actually now in the interim drawn in all the nets on the PCB. So you can see I've connected all the points together. A couple things I will just point out, and we did mention this earlier, that where, for example, we have a wire link connecting two pads together or two areas of pads on the schematic, you may not be able to draw the net because, as we mentioned, and Det mentioned Ghostbusters, you cannot cross the lines. So in that case, you'll see here, all I've done is added a net on the other side of the board. Now do that here just by simply selecting layer 1 or layer 2. So that's the blue one you see there. And another good example, because you saw it earlier, there's a wire link from here to here. Again, I can't draw the net unless maybe I did manage to go around this way. So I just put it on the other side of the board. And if we were producing a PCB from this one, this is how we would produce it. Double-sided costs the same as single-sided, so why put the wire links in? We would just put tracks on the other side of the board where these blue ones are. So you can see I've put all the nets in, and if we go to the schematic, all of our components now have net names on all of the terminals. Now, although this doesn't look anything like one, this is actually a schematic. We know, looking at this, where every component is connected to. The pin here of this capacitor is ground, this one goes to net 4. And if we look around, we can find the other things that are on net 4 and say, okay, these points are connected together. But that isn't really a human understandable schematic. So what we need to do now is to rearrange these components. We need to find, for example, all the points on net 4, and where we can, position the components next to each other or near to each other in some sensible layout. And then we can delete the actual labels, N4, and just draw wires between them. This actually is a little bit easier than you might think, because you're thinking, okay, where is N4? And you're hunting around. Okay, I can see there's an N4 there, but I'm having to look around to see where that capacitor connects to so I can draw the lines. If we go back to the layout, as we discussed earlier, when you click on something on the net, it automatically shows you where it is. So you know this end of this component is hot ground. And if I connect to something else, it shows me again. So I don't have to, and you don't have to, hunt around. You can use the nets you've drawn on the PCB to easily find all of the components that are connected together. Actually, my rather sharp-ish eyes have noticed there is an error, at least one, on my schematic. You'll see here LF1B1 only has one net attached to it. We don't know where the other end's going. It should go somewhere. Now we could look around on the layout and find the component to see where it should connect to, but the little trick I showed you how to find the components by clicking on the layout works the other way around. So if I go on to LF1B1 and just click on it, we can see it's there. And we can see where the missing net is. There's something here, yeah? And we can follow that. So we can see, in actual fact, this is N8. So the end of this choke, this one should be on N8. I can now add that both to the layout and the schematic. I'll do the schematic first this time, but it really doesn't matter. So we can go with N8. Okay. And we can add our net. Click W. This is my way, you know. We can connect that to there. And we can also fix the layout. So on this one, left click, right click, properties. And we can see it's unconnected. So we will go with N8. Okay. That is now N8. And you see the rat's nest, the little blue wire. We can now easily draw this in, making sure, as I mentioned, we're on the correct layer. Okay. We go to the net and we just draw it in. And there it is, guys. So that has fixed that both on the schematic and layout. Okay, so that little mistake wasn't on purpose, I will say, guys, but it's probably taught us a few useful techniques. Now, let Det show you how to take this jumble of components, which is a schematic, and make it look more like a real schematic.
All right, guys, back on the mouse here. And yeah, I developed the code over the weekend. So if you follow my video channel, you know I'm sounding like I'm dying here. I don't. Promise, I don't. This will get better. Some months in the future, it will get better. So please excuse the rough voice. All right, but we're here to not talk about my voice. We're talking about this schematic over here. This humble mess over there. Richard was very, very busy over here doing all this stuff. And believe me, this isn't the easy part. You have to do a lot of work to get this all done here. Let's start with it. Okay, first thing I want to do, I want to move all this mess over here. I want to move it out of this thing over here. So I mark everything, and I just see I already missed here something. And what you can do with all the components, you can move them. You simply grab them and drop them somewhere.
Yeah.
Where you like. My normal position would be somewhere on the right here.
Okay.
So I have my drawing space here. That's where I want to put the schematic after that. So where do you start with this mess? Well, you could simply grab a component, drop it onto the other side, and try to populate this schematic. Believe me, this wouldn't work, and it would be a second mess here. What we can try to do, we can go, where's the input, where's the output? Because this is a power supply. There has to be an input, stuff happening, and there should be an output.
Yeah, and actually this is a convention, guys, with schematics. So when you look at the schematic, almost always the input is on the left-hand side of the schematic sheet and the output is on the right-hand side. So the signal, the flow, or whatever the schematic is doing would normally go from left to right.
Indeed. Our input is the J1 over here. This is the first terminal where the mains is coming in. So I'll grab this one and move it over to my schematic. Yeah, I have to do this in 2 steps. Don't worry about this.
Okay.
Now I have 2 nets. I have N3 and I have N2. Richard was showing us the thing where you switch over to the PCB editor and simply select the trace you want to have. You can do this a second way here, and please use the way you like. This is not a better way, this is simply a different way. You can use find, because it's a computer, it finds stuff. So Control F, then I can say I want to look for, what was it? N3.
N3.
So I type N3 in here and let it select. You see N3 over here is already selected, tells me, okay, there's one thing that's net N3. If I find the next one, simply find again, I see, oh, look at this. This is the next one. And now I simply grab this one, move it over here. I know I want to use it somewhere there. I don't have a clue where I want to use it, but I want to have it over there.
And there are several more as well.
Yeah. So here's a N3, and this is connected to this little cap. So I select this. Now I have it.
Okay.
So I'll zoom out a bit, and then I move it over. And move it over again and drop it over there.
Okay.
Not an idea where I put it. This is simply to collect every part that we have connected to N3.
And we have 2 more, I think, over here.
We do. And now I see them. Sometimes this is easier, just simply looking for them.
Okay.
So I move this over. Come on.
Yeah.
And I move this
The
over.
last one.
Yeah. And there's another one with N3 on it. So
Okay.
go over here and moves this over there.
Okay.
So I don't need to find anymore. You see, I left it open all the time. You can simply let it float over there. It will always tell you, look at this, N3 is here, is here, is here, is here. So you have a very good idea where all the components of this net are connected. So let's move the components around a bit and see what's happening over here. So the other parts are connected to something like N1, and there's even more N1. There's a lot of N1, you see that?
Yeah.
So I think it's probably a good idea to see what's on N2. I guess that N2 will come somewhere. So let's see what's on that.
Yeah,
one.
I think actually because this is an input, the first thing will be a fuse. So the chances are there was a fuse from N2 feeding to N1. And then these are filters and chokes.
Yeah, let's see this.
Okay.
So we can simply use N2 as a search over here. N2. Oh no, you have caps lock.
Okay.
Go. And 1 and 2 is over here. That's right. find, and then there's a fuse.
There's your
excellent.
fuse. Okay.
There's your fuse, man.
Okay. So really, guys, a little bit of an idea of the layout of a power supply is obviously helping here. You can do this without the knowledge, but a little bit of knowledge is often useful.
Indeed, it is.
And sometimes dangerous. As we all know with electronics, guys.
What could help? If you have the PCB lying around, you can check on the PCB if you're not sure where should this be going.
Yeah.
And the fuse is the obvious culprit over here.
Yes.
So let's get the fuse in here. And from there on, it should be way more clear what's going on here.
Okay.
If you're wondering how do I zoom in and out all the time, so this is simply just the mouse wheel. Just turn the mouse wheel and it's moving.
Okay. So looking at this diagram, I would say the fuse should be horizontal.
Yeah.
And the choke should be horizontal because that's in line with...
Oh, yeah.
Yeah.
Right. The choke would be more like
this.
Yeah.
And there will be another half of this choke too.
Indeed, yeah. Let me connect these first so we can see where this ends.
Okay, perfect.
So N2, we only have 2 times. That is the logical explanation over here.
Yeah.
So let's connect those. I know I have all my N2s over here. The net is complete with that. So what I can do is I can simply erase this. I can remove this. I can remove that. And now I think I have to remove these and remove this.
Okay.
Rotate this one.
Yeah.
Move it somewhere here.
Yeah.
Get a wire.
Which is W.
Yeah, indeed. And get a connection like that.
Ah, okay.
So now we have N1 over here. And you see lots of components are simply going down N3 to N1.
Okay, yeah.
N3, N1.
And 3 and 1.
Yeah, let's do this.
And another one. And 3 and 1.
Beautiful. As far as possible.
Okay.
So, yeah. Okay, you maybe want to speed this up because now I have to connect all the little dots.
Okay. Well, connect all the M1s together. This is the thing now, yeah?
Yeah, indeed.
KiCad really does not like that, by the way. They're not really compatible, we've noticed.
No, we're not.
So you can see there we have the beginning of a schematic, and the process from now is just the same we've been showing you. Because again, this is a long process, we will now show you one that we have prepared earlier.
Before we do that,
okay.
let me show the guys one thing I really stumbled upon and would really bit me in the neck.
Oh, okay then, guys. That show us what have you found.
This is not KiCad's fault. This is important to know. This is not the fault of the software. It tries to be clever here, but sometimes cleverness is not appreciated.
Right.
We have some resistors in here that don't have the normal resistor numbering over here.
Oh, like R105, for example.
Yeah, you see this one is R105. So what I love to do with all this stuff, because I hate the moving part around. So normally I'd go for, okay, let's grab this, do I have it, and use Control X.
That's cut.
That's cut. That's not copy, this is cut.
And it's not delete, it's just cut. It's now on the clipboard.
Right, it's in the clipboard right now. Okay. And now I move to my schematic over here and simply paste it over here, Control V.
I see what's happened.
Yeah. And you may remember this thing was called R105.
Yes.
It isn't anymore.
Oh.
And in this moment, the connection to the part on the PCB is lost too.
So this is not what we want.
This is absolutely not what we want.
Okay.
So please don't cut. This isn't the fault of the software. This is simply, it tries to be clever here, but it simply kills the connection to the footprint. So you can't update after this anymore. Not the best way to do that.
Okay, so we have to pick up and drag.
You have to pick up and drag. So sorry for that, guys.
Okay, of course, Det didn't do that with an entire schematic, by the way, because that wouldn't happen. Yeah.
No.
So let's show you the one that is nicely arranged.
So by the magic of video editing, suddenly everything is in place. Well, more or less. So we have page 1 over here, and we have a second page over here. This is page 2. I simply try to use 3 function blocks in here. this is the input stage where you see the bridge rectifier, and I called it mains high voltage. You can use these boxes over here to get it a bit more nice. You see, I lost interest after the first box. Sorry for that. That depends on how much self-explanatory is your schematic over here. I think mains high voltage, you see this is mains high voltage.
Okay.
And you also see I didn't get rid of all the nets. I kept my GND net, my ground net. I kept hot ground. I kept
HT, high tension.
High tension, yeah. I kept HT, so these we'll find these a bit later in the show too. If you're wondering what is these, what are the chokes, this is the way we drew them because we don't have the footprints for them. We simply threw in some chokes over here. This is in fact one unit here, and the transformer is looking strange too because this is the secondary of the transformer, and this is a primary of the transformer. So we could have done better here.
I think I would have drawn the transformer more like a transformer with a primary and secondary. But then debt isn't me, so different ways. So this secondary, which is going from ground through a resistor through this diode to VCC, this is the one that keeps this pulse width modulator running, okay? So when we power this up, HT, 320 volts, feeds into the drain. This will have effectively an internal high value resistor from here to VCC. Effectively. So this generates its own startup voltage. Once this gets going, it then generates its own supply voltage. And that's actually normal for power supply. So, Det, you've done something right here. I would have just laid it out a little bit different. And seeing as Det is dying today, and he's a rather useful guy to keep around, so I'd rather him not die. How do we get to page 2?
You simply click over here.
Page 2. Okay, so this then is the output side. So again, this is part of the transformer. This is the other secondary, one end connecting to ground and the other connecting to the anodes of the two diodes, the Schottky diodes, which then produce the output, the 12 volts. These are your smoothing capacitors. And this is your output. This is your 12 volts out, okay? There's a rather strange network here, guys, actually. We've looked at it, it is wired like this. So for some reason, from the AC output of the secondary, the 12 volt output, we have a 10 ohm resistor and a high voltage 1 nanofarad capacitor. We think this is some sort of snubber network. A snubber network is there to reduce noise. But we would have thought that would go to ground, but looking at the board, it definitely goes to the 12 volt output. So maybe some of you guys know a bit more about PCB design. Why did the designer do it that way? I can't see why it wouldn't work that way, because really from 12 volt out to ground at high frequency is effectively short. Yeah, but interesting maybe why they did that, unless they wanted to use this inductor as well as part of that snubber. Maybe. We're not experts on this, but we do know how to create a schematic from the PCB, and now so do you guys. Just to finish this off, by the way, we have the voltage reference, the TL431. This resistor network is sampling the output, the 12 volts, and it's connecting to the reference pin on the TL431, which effectively makes this turn on when that reaches 12 volts. This will turn on. In fact, if you look roughly here, we have a 40k and a 10k. So the voltage here is 20% of the output, about 2.5.
Yeah, it must be, yeah.
2.5. Somewhere around that. And the TL431 is a 2.5 volt reference. So there must be good reasoning for that. So the idea with this resistor is the current limiter for the LED and the opto-isolator. For the opto-isolator to turn on, this must turn on. And that's what is happening. So that little network of resistors there is setting the voltage here at which this turns on. Okay. Once it turns that on, you can see some more labels. NFB, this is network feedback, as I called it. And that comes back into our pulse width modulator on the feedback pin. So that's effectively controlling the width of the pulses going to the transformer. Okay. This one, by the way, is a current sensing resistor. It might look a little bit strange, but internally, this chip also has the MOSFET driving the transformer. So the current flows from HT, 320 volts, through the primary into the internal MOSFET. This is switching on and off rapidly. And the source effectively goes to this pin, CS, which goes via this resistor to ground, this low value resistor. And the chip internally is also monitoring the voltage on here. And by measuring the voltage across this resistor, that's how it knows how much current is flowing through the transformer.
Clever little chip. Clever little chip, man.
Okay, guys, so we definitely have a usable schematic here now. Now, that really is the end of this saga, or at least part 2. We have achieved what we said we were going to achieve, which was to show you how to create a schematic from a PCB layout. But seeing as we are here, we just thought we'd show you one or two other things. So this is our PCB. Now, we've created nets that match all these tracks, where the tracks are going. So if we wanted to make a PCB from our schematic, we could do so. But what we wouldn't have is all these wide areas of track in the ground plane, in the power plane. You can clearly see that where a lot of current is flowing, it's going through thick, heavy tracks. So what Det will just show you now is a little Easter egg, if you like, at the end of this, is how to create a PCB layout where the tracks look like this.
So while we were creating the layout, we didn't think about track width or something. We just go for, okay, there's a connection from this one to this one to this one to this one. Especially for PCBs like this one, this is a power supply. It's vitally important to get the tracks in a certain width. Because we want to send some power over them.
So really, there's a direct relationship between the thickness of the track and the current it can handle.
Indeed it is, yeah.
And also, I guess, the resistance it has at that current.
Indeed, okay. Absolutely. There's another factor over here that has something to do with frequencies, but not on this board. And you don't want to go there.
Okay. Okay.
So how do you do that? One thing would be to select the track over here, and when I press U, I select the whole track.
Is that letter U?
Letter U, yeah.
Okay.
And then I go down here to track width, and I can change this. I can say, okay, give me a track width of 60 over here. And you see, oh yeah, this is a nice fat track. We could use it. But it doesn't have the shape of this thing over here. So I now do want to have the shape over here because there had to be a reason to design it this way. But there's an easy way to do this. And this is a polygon over here. You see the polygon, I have to be on the right side. And what I'm going to do now, I simply follow roughly the track that I'm having over here. Just move it over here, move it over here, move it over here.
So you're just clicking the point on each corner, effectively.
I was going to say it's just like in Photoshop, but you hate me for that one.
Okay.
Going over there, going over there, going over there. Yeah, I know, we don't need this because this is not populated, but bear with me. So, and now we have this thing here.
Okay. And it's there. And now we can see the nets, the ends of the components where the holes would be drilled through, and our nice fat track.
Indeed, yeah. So you have the same or the equal thermal capacity over here, and you have the current capacity over here too.
Okay, so if we create a Gerber file from this to manufacture a PCB, would we then be able to upload this to PCBway and just create the PCB that looks like that?
Sure.
Oh, excellent. Yeah. Excellent.
Yeah. This is the idea with all this stuff, because this would be a copper fill over here, and in PCBway, this is really good over there. You can use different weights of the tracks, so you can choose. The normal one would be 1 ounce for a track. You can go up to, I think, 12.
Yeah. Oh, that's really
sounds like this. Sounds
this
like
big. Yeah. Okay.
Sounds like the PCB would be double the size or something like that. We should try that.
Yeah, we should try that sometime. So that's what the number of ounces does. It actually selects how thick the tracks are.
Yeah.
The thickness of the metal.
Yeah.
Okay, guys. So I think now we have hopefully achieved what we wanted to do, which is the ultimate guide to designing a schematic for a PCB. But as you know, guys, ultimate is a very difficult thing to achieve. So we are calling this part 2. We are saying this guide is complete for now. However, there is more to this topic. So I'm sure at some point in the future, you will see Det and myself back with a part 3 and so on. Okay, so I'd like to say thank you very much again to Det for crawling off his deathbed to come in today. Okay. Drag him back on. I'd also like to say thank you very much to PCBway.com for sponsoring these videos. Without their help, we would not be able to do this. And finally, I'd like to say thank you very much to all you guys who make the whole thing worthwhile. Let us know what you thought about that. Get into the comments below. It means a great deal to us. And we look forward, Det and myself, to seeing you all soon again on another Learning Electronics Repair video. Ciao for now, guys.